Okay, so let's calculate the forward kinematics equations using the DH convention for a cylindrical manipulator. So here you have the first joint to be rotary, and then you have a prismatic that goes up and down, and then you have the other prismatic that goes left and right. And then right now, temporarily, I attach an end effector. So here I assume that all you have is just 3 degrees of freedom, and then the end of it is going to use an end effector to interact with the environment. But later I'm going to calculate the forward kinematic equations for a spherical wrist, and then instead of this gripper, I'm going to attach a 3 degree of freedom spherical wrist, so make the total degrees of freedom for it 6 degrees of freedom. But right now, let's just assume we only have 3 degrees of freedom here. Okay, so step number 1 is determine the axis of actuation for each joint. So for this one is rotary upward. So clearly I can say that this one is going to be my Z naught. This one also is similarly upward. So for this one, I can say this is axis Z1. And then the next one is going left and right. So I can say, for example, for this one, this is Z2. We'll take care of the end effector later. Let's just for now focus on the first three, the robot joints, basically, no end effector. So that's the Z's. Then it says determine the origin of the frame 000. Determine that arbitrarily, right? Basically means put the origin anywhere you want along the Z naught, and the direction of X naught and Y naught are completely also convenient selection. So here you have no limitation of what and how to select X naught and Y naught. Definitely one of them has to be out of the plane because Z naught is in the plane, and one of them is going to be horizontal, so it's completely up to you. Here I choose my origin to be here at the center of the joint, and my X naught to be out of the plane toward me, and then my Y naught to be basically to the right. Then here it gives a rotation with angle theta 1, correct? And then you go to the next joint. Now for the next joint, as I said, the origin and the x-axis have to be determined by the DH convention. So if you look at Z0 and Z1, they are parallel. Therefore, the location of the origin for frame 1 can be anywhere along Z1. But the important thing is X1 has to be perpendicular to Z0 and intersecting it. And so I can select X1 to be either this one or this one, because both of them are going to intersect the extension of Z0, and both of them are going to be perpendicular to it. And as I said, to avoid twisting and to go with minimal parameters needed to represent the robot, I prefer to make X1 to be the same as X0 and Y1 to also be the same as what? Y naught. That makes life a lot easier for me, right? Because there is no rotation involved. Good. So this is my frame 1. You clearly see that's where I select point 0.01 to be. This is point 0.0. Then I go to the next one. This time my Z1 and Z2 are already intersecting at this point, correct? If you continue Z1, you see it is intersecting Z2 at that point. And so according to what we learned in the previous slides, this is going to be my origin for frame 2 already. So that is set. Good. So that is 0.2. I got it. And so I have to now draw X2 such that it is perpendicular to Z1 and normal to it. And again, I can select it to be only this direction. Why? Because if I do it like this, then it is not going to be intersecting Z1. It is going to be what? It's going to be parallel to Z1. So here I have no solution other than saying this guy is my X2. Okay, and now with that being X2 and that being Z2, the direction of Y2 is going to be downward, because again, if you remember, each frame has to be basically right-handed. So there we go. I got my Z1, I got my Z2, Y2, and X2. Good. So everything is set. So the first 3 frames are set. Now let's look at the end effector. For the end effector, the direction of X, Y, Z is not really, because here, if you use the NSA approach, then Z has to be the approach direction. So Z3 has to be something like this. And then we have to set up the X3 and Y3 such that X3 is perpendicular to Z2 and intersecting it. And if I do it vertically upward or I do it out of the plane, both of them can do the job. And well, to again avoid rotations and go with minimal representation, I'll choose my X3 to be the same as what? X2. And therefore my Y3 is going to be downward, so no rotation between them. Good. So this is going to be my origin 3. Y is clearly the direction of the slip, which is the opening and closing the gripper. Z3 is the approach direction, and X3 is the normal. So here you see I'm completely observing that NSA rule that I mentioned, but I did not have to necessarily do that. The only thing is X3 could not be the same as Z3. Okay, definitely, because then it would be parallel to Z2. It has to intersect it and be perpendicular to it. So any of these 2 guys could be X3. But if I want to go with that NSA convention, right, which is, or SAN, let's say, right, it has nothing to do with the NSA in the government or anything. So SAN, right, or ASN actually, approach, slip, and normal, then this is exactly matching that. So these are my frames for the DH convention. And now it is time to go and insert our table. So what we need is a table, and here we have 3 parameters to choose. So what we really need is, the columns is always 5, but here we need really 4 of these. So that is my DH table. Let me get it out of the way. And here, so this is going to be 1, this is going to be 2, this is going to be 3. Let me see if I can resize this table so it gives me a little bit more room. Okay, so now I can say this is 1, this is 2, this is 3, this is theta I, this is di, this is ai, and this is alpha I. Okay, and then try to fill the DH table. So the first one, the first row, relates basically your frame 0 to frame 1. If I want to go from frame 0 to frame 1, what do I need? Do I need to first rotate? And the order we go is always theta, dA, alpha. Do I need to rotate? And you know, these 2 are about zi minus 1, and these 2 are about xi. So d1 and theta 1, which are about or align z naught. First, do I need to rotate anything about z naught to align x naught to x1? Yes. Again, if you look here, you might say no, but you know there is, because again, I'm looking at this manipulator from what? From only one view. What I really need is to look at this guy from the top. If I look at this from the top, this is going to be the rotary joint. Z naught is going to be out of the board toward me like this. My x naught is going to be like that. My y naught is going to be like this. Okay, so this is my top view. And then right parallel to the right along the z, if you move for this distance, which is from O0 to O1, and I call it A or A1. So A1 is the length from here to here, this length here, I would call it A1. You go up so you cannot see it because it's perpendicular to the board, but then you have to rotate for X1 and Y1, so your frame X1, Y1 looks like this. So this Z0 is also the same as Z1, Correct. Let me make sure. This is Z1. I have to avoid typos. So this is, as I said, also the same as Z1, and then here is Y1, and here is X1, and this angle is theta 1. Okay, so clearly you see that I need a rotation with angle theta 1 about positive Z0 to align X0 with X1. So yes, absolutely, I need a rotation, and that is theta 1. Then do I need to move along the old Z to go from O0 to O1? Again, absolutely yes. I need to move a distance of A1 along it. So this is going to be A1. Do I need to now move along the new X to put the origins on the top of each other? No. By just moving along Z0 a distance of A1, they are already on the top of each other. No extra displacement is needed. 0. And then do I need to now spin or rotate about the X1 axis to align Z0 and Z1? No, they're always upright in this front view. They're always vertically upward, so they are already aligned, so no twist is needed. So if you look here, this is my first row. Now, one thing is between A1 and theta 1, which one is variable? As I told you, it's the theta, the joint variable, and I put an asterisk next to it to tell you that that is the joint variable. A1 is constant. The other important thing is A1. Don't think that just because I called it A1, it has to be under AI. No. The definition of AI is the displacement along X, along the new X. But this A1 is displacement along old Z. So I have to put it under the D value. So don't think just because I call this N, A, that should be also under A. I could call this something else. I could call it L1, right? If it's confusing, here we go. I call it L1. No worries. I would call it L1. Okay, so we have to make sure that nothing is confusing us. There we go. Now, for the second row, I go from Z1, X1, Y1 to Z2, X2, Y2. First thing first, do I need to rotate about Z1 to align X1 and X2? You clearly see no. Here, there is no rotation involved. This joint, all it does, it goes up and down for a distance of D2. This is the prismatic variable of the joint. But the X's are already good. They are in the same direction, so no rotation is needed. Do you need to move along the Z1 to go from the one origin to the next? Well, absolutely, that's the distance D2. When the origins are on the top of each other, then no, of course, displacement along X2 is needed, so A0. Now, do you need to twist about X2 to align Z1 and Z2? Yes. If you see here, this is your Z1, this is your Z2, and this is your X2. They are not aligned. What you need is rotate about this X2 a 90-degree angle to bring Z1 on the top of Z2. And since X2 positive rotation is counterclockwise and this rotation is clockwise, so yes, you need a twist of negative pi over 2. You get negative 90 degrees to make the Z's align. Okay, so that is very important that we recognize it, that there is a twist involved. Good. Now that I got this one, I go from the second frame to third frame. Again, for this one, the joint variable is D3, which is the prismatic. By the way, in this second row, the only variable is D2, that negative pi over 2 is constant. So now what? Now what I need is to go from origin 2 to 3 first. Do I need to align the x's? If you look at the x's 2 and 3, they always stay there. There is no rotation about the joint here involved, so there is no joint angle. Then how much do you need to move from origin 2 to origin 3 to get there? That's this variable d3, the prismatic joint variable. And the next question is, okay, now you got there from here to there, good. Now and here I better put my origin right at this point, not at the center of the wrist, so that this whole length, if I can change it, you know, it is representing D3. Because if it's in the center of the wrist, then a portion of that D3 cannot be really changed, right? It's a fixed distance between the center and the beginning of the wrist. So I would put my origin right here. And then I go with what I had. So I make this Z3, and then it was this guy, which was X3, and then I had Y3, right? So this one was Y3, then I had X3 and Z2 here, okay? So I'm just trying to write it as clean as possible. Good, so clearly now if I'm able physically to make this distance 0, that means I can completely use D3 to go from O2 to O3, good. Now, do I also need to move along X3? No, no displacement is needed anymore. And is there any twist? Do I need to rotate about X3 to align Z2 and Z3? No, they're already aligned, so no twist is needed. So that is my DH table. It is all set. And now I can go ahead and form those A matrices. And again, if you want, I can bring that formula for it, which I guess it was this guy. Let's bring that in. It was this one. And now I have to apply 3 times, each one for one of the rows, to get my A matrices. So first we look at row number 1. If you do it, it gives me my A1 matrix, plugging the parameters here for theta, dA, and alpha. I should get C1 negative S1 0 0, and then S1 C1 0 0 0 0 1 L1, and then 0 0 1. Which completely makes sense. As you can see, the rotation part of it is a rotation Z with angle theta 1, which completely makes sense. And the displacement of it is a displacement about Z axis with L1 units, which again, you completely see it does make sense. So that completely meaning. So this is R of 1 with respect to 0, and this is D of 1 with respect to 0. Then we go and look at the second row. So this time we're going to go look at the second row. That gives me A2. And A2 is going to be 1 0 0 0 0 0 1 0 0. Then here we are going to get negative 1. Then 0, and then D2, and 0 0 0 1. Okay, you see, if you look at the rotation part, there is no angle involved, so it's a constant rotation, but it doesn't look like the identity matrix. The reason is there is a twist involved. Okay, there is a twist involved, so this is r of 2 with respect to 1, and this is d of 2 with respect to 1. Now, does this r of 2 with respect to 1 make sense? Sure. The first column is telling me that x2 is the same as x1. You can see the only component is the first one, so x2 is the same as x1, right? Let me write it for you. That means x2 is the same as x1. That's how we interpret this. The next one is telling me what? This is for y2. This one is telling me that y2 is negative z1. You see, because the z component is only there and that's negative. And this last one is telling me that z2 is what? It is y1. Is that right? Let's go look at it. Look at it. If you see clearly x2 and x1 are the same. If you see y2 is negative z1 and z2 is what? y1. So you see clearly those columns, each one had a very clear meaning, which is exactly according to what we can see. And finally, you go and look at the third row with this formula for A matrix, and A3 is going to be 1, 0, 0. Your rotation matrix is exactly identity in this case, and your displacement is simply 0, 0, D3. Of course, because if you look at the frame 2 and 3, there is absolutely no rotation, no twist, no nothing. So the rotation has to be an identity matrix. And d of 3 with respect to 2 is only determined by the prismatic value, joint value of d3. So now that I got a1, a2, and a3, finally I go ahead and multiply them all together, and that will give me what? That will give me the H matrix or T matrix, whatever you want to call it. If we go with the notation we use here, we can use T notation, but that's the same as the H notation. So T of 6 or 0, which is the same as H of 6 and 0, 3 and 0, not 6. There is only 3 here. 3 with respect to 0, which is the same as H of 3 with respect to 0. This is of a form R3 with respect to 0, D3 with respect to 0, 0 and 1, where this is a vector 0. Now, if you multiply these three matrices using the symbolic toolbox, the result is going to be C1, 0, negative S1, S1, 0, C1, 0, negative 1, 0, and then negative S1, D3, C1, D3, then D1 plus D2, where in this case actually it is not D1, it's L1 plus D2, because L is that constant length, and then you have a 1. Okay, so clearly this is your rotation matrix, which is only a function of theta 1. Clearly you see only theta 1 is affecting it, but the displacement, the position of the end effector with respect to base, that is a function of theta 1. You see the sine and cosine of it here. It is a function of the D2 and D3. So it's a function of all three joint variables plus this constant L1, okay? And if you look at them geometrically, you see that they all have complete meaning and sense, right? Just let's look at the displacement, for example. It says the Z component is L1 plus D2. Is that right? Yes. If you look at the coordinate of the last origin, which is this one, with respect to the first one, so end effector with respect to base, you see that along the direction of z naught, how far should I go up to get there? It's this L1 plus what? Plus D2, so it completely makes sense. How far should I go along the x naught and y naught to get there? It says it is D3 times what? Sine and cosine of theta, where the x is negative sine theta and y is cosine theta, and that you can clearly see from this top view. So if you look at this top view here, as I told you, frame 1 is like that. If I want to draw frame 2 has what? It has Z2 to be in the same direction as X1, so it is going to be Z2. And then, let me make sure. No, it's not right. X2 to be the same direction as X1. Y2 is downward, so your Y2 is downward, and then Z2 is the same as Y1. So this Y1 is the same as Z2. And then this guy here, this cross, which is inside the board, that is Y2. And finally, if I look at 3 has the same as 2. The Y's are the same. The Z's are the same. The X's are the same. Okay? With one difference. What is the difference? So the 3's are not exactly like that. I have to change it a little bit. Why? Because now you have a prismatic D3 that comes out. D2 you cannot see from the top view, okay? It's perpendicular to the board, you cannot see. But D3 you do. So although the orientation of X2, Y2, Z2, X3, Y3, Z3 are the same, but there is a displacement of D3 along Z2. So this is Z2. So let me get this somewhere else where I have a little bit more room. So what you really have is along this direction Z2, you have some distance D3, so like this, for example, where this distance is D3, and okay, too much to squeeze in one place, but that's okay. So this is Y1 and Z2. So you first move a distance of D3. You come to that point. Now the Z's are the same. Let me use a different color for this frame. Now the Z's are going to be the same. The X's are going to be the same. And the Y is going to be perpendicular to the board inward. Okay, so now clearly that D3 has to be decomposed with this angle theta 1 along what? X naught and Y naught. You see the component of that D3 along Y naught is D3 cosine theta 1, which you can clearly see it here. Here. And then for the X naught, it should be D3 negative sine theta, which again you can clearly see. Because when you decompose this D3 along the X naught, it is going to be decomposed along negative X naught, which is this guy. Okay, and this distance here is D3 times sine theta, but theta 1, but it is in negative X naught direction. So that's what you can see that. Okay, so you see, it absolutely does make sense. That's all it is. Okay, so here we have seen the cylindrical manipulator, the forward kinematics equations for it, the rotation matrix as a function of joint variables, and the displacement vector for the end effector with respect to the base as a function of the joint variables. Good. Now let's practice one more thing, and that is the spherical wrist. As I said, spherical wrist is basically allowing you to have 3 rotations along 3 different axes in general, and the angles of this are actually very similar to the Euler angles. I'll show you. And you can basically create any orientation that you want for the end effector. So by adding this spherical wrist, you're going to make your robot dexterous. Okay, for example, if we put it on this cylindrical manipulator, you see here the end effector is not dexterous because the only orientation it can take comes from this theta 1. But when I bring this spherical manipulator here, you have 3 rotations that allow this end effector to take over any arbitrary orientation, right? So that's the advantage of this. And it has other advantages when in future videos we go to inverse kinematics. I'll talk about it. Kinematics decoupling is one of the things this wrist allows. So that's why most of the robots, when they want to replace their end effector, let's say gripper, with something that gives them dexterity, the end effector they choose really is added to a spherical wrist. So they have a spherical wrist to not only make their robot dexterous, but also to make calculations of their inverse kinematics equations, as we'll see later, easier, but what we call the kinematic decoupling. So for now, all it is you have first a rotation along this axis, followed by a rotation about this axis, and then followed by a rotation about this axis again. Okay, so you have 3 rotations. That's what the spherical wrist does. And now our goal is to set up the, again, the DH convention axes, find the A matrices, multiply them together, and then we can get the orientation and the position of this end effector here with respect to the frame that is attached to the first joint of the spherical wrist. Okay, so now the explanation of this is quite interesting. First thing we do, we put the z-axis on for the first 3 joints. Forget about the end effector right now. So what we do is this. We set up the z-axis. So this is going to be the z-axis for this guy. This is joint number 4, so the axis is going to be z3. This is joint number 5, so the axis for it is going to be z4. And this is joint number 6, so the axis for it is going to be z5. Okay, so first thing, set up the z-axis. Then go ahead and start with the origin of the first one, which is arbitrary, and then the x and the y for it. Now here is the thing that we have to do. As it clearly says, I'm completely in charge of deciding where to put origin number 3. I can put it anywhere along Z3. Nothing is going to limit me. It's just based on my decision. So you might be tempted to put it here, which kind of makes sense, right? You typically always put it at the center of the joint. But what they do to make life very easy for analyzing this spherical joint is, instead of putting it there, actually they come and put it right here. Remember, I told you one of the properties of a spherical joint is that in general, the 3 axes of rotation, Z3, Z4, and Z5, they all intersect at one point. Okay, because in general, when this guy rotates and this one rotates and this one rotates, it's not like Z3 and Z5 are parallel. No. you know that if this one rotates, and especially Z4, the middle angle rotates, if you look at this from the top, what would you see? So if you look at this from the top, you'll see that you have this one, but now because this one has rotated, okay, then what you will have is, just trying to give you a nice picture if I can. So it's not going to be like this because this guy can rotate, so it is going to be a little bit tilted, so probably something like that. And well, not that bad of course, but probably something like this. So what is this one? What's the difference between this one and this one? This is like that, but rotated about this angle theta 4, okay? So this spin a little bit about that axis, and now, so the these two lines, this guy here, I want to draw that for you. So that will also be something like this. Let me see if I can move this a little bit out of the way for you. And then about this, you have a rotation. So this guy does not have to be like that. This guy can also rotate, and if it does rotate, then you will see basically something like this. And now attached to this, you have the next one. And then with respect to this, the end effector can also rotate, so it doesn't need to be like that. It can be a little bit twisted like this. Okay. Or it doesn't need to be just that perfect, so it can be just, by perfect I mean perfectly 90 degrees rotation. It can be something like that. So this one is also rotated. So here you see this one, there is a rotation. You see this one, there is a rotation. And you see this one, there is a rotation. Okay, so definitely the three axes, Z3, Z4, and Z5, are not going to be the same way that you see from this view, because now your Z4 is like this, your Z3 is like that. Let's see if I get rid of those rotation. Your Z3, as I said, is like this, and your Z5 is like that. Okay, so it's not like Z3 and Z5 are always what? Parallel. And if you continue each one of them, extend them, you see they all intersect at one single point, which is here. This point, which we call it the wrist point, this is the intersection of the Z3, Z4, and Z5. And in this case, I'm trying to select that point to be the origin of all frames 3, 4, and 5 to simplify everything. So instead of me putting the origin of Z3 is the X3, Y3 at the middle of the fourth joint, I'm going to put it in the middle of the fifth joint. Because the Z3 is a free vector, so I can bring Z3 here if I want. Correct? It's just a direction. That's all that matters, the direction of it. So now I put my Z3 there and origin 03 there. Good. Then what? Then X3 and Y3 they're completely up to me. So I decide my X3 to be like this. And based on that, you clearly see that your Y3 has to be downward. So this is frame 3. Now for frame 4, my Z is like this. That is Z4. Okay, and Z3 and Z4 are already intersecting at this point. So that is going to be the origin of frame 4 as well. Now my X4 has to be such that it's perpendicular to Z3 and it is what? Intersecting it. So it could be any of these. It could be the same as X3, it could be the same as Y3 because they both intersected and they're both perpendicular to Z3. And again, to avoid rotations, I pick my, to make it simpler, I pick my X4 to be the same as X3. Right? Now Y is going to be different, correct? So Y is clearly going to be to the right. So clearly you see X3 and X4 are the same thing. Z3 and Y4 also the same thing. Good. So I got my frame number 4. Now I go look at frame number 5. For frame number 5, again, Z is the same as Z3. So Z3 and Z5 are the same thing. My X5 has to be perpendicular to Z4, intersecting it. And if you look, my Z5 and Z4 also again intersecting at this point. So I can say again that point to be the origin of frame 5 too. So while this one is Z5, now I have to select what? X5 perpendicular to Z4 and intersecting it. So good, that is Z5, perfect. Now, again, I choose this direction here, the very same direction as the rest of the X's to also be X5. Okay, so this direction is also X5. And now with that one be Z5 and this blue be X5, now my Y again has to be the same as Y3. So this is going to be the same as Y3, Y5. Okay? So these three, which are the same, are X3, X4, X5. These two guys that are downward are Y3 and Y5. And these vectors that are all to the right side, they are Z3, Z5, and Y4. The only thing different from the rest is Z4, which is upward like that. Good, so this is how I set up my frames. Now that I'm done with frames 3, 4, and 5, it is time to go and look at what frame? Look at, of course, frame 6, the end effector frame. Okay, what can I do about that? So let me choose a different color for this one. Maybe like this color. And for this, again, can I use that ASN approach? I guess I can, as if I choose this guy here to be my Z number 6, then my X number 6 has to be perpendicular to Z5 intersecting it. And since Z5 and Z6 are parallel, I can choose the origin to be anywhere I want here. I choose it at this center of the wrist. And I choose my X6 to be the same direction as X3, 4, and 5. Like this. And with that X and that C, it means clearly my Y number 6 is going to be like this. Okay. And then here I have this distance, which is from the center of the wrist to the center of the end effector. So this distance from here to here, I call it L. So this L is the physical distance from the center of the wrist to the center of the end effector. And this point O here, that is O3, O4, and O5. They are all at the same point, which, as I said, again, I call this point the wrist point, or the wrist center. Okay, now that I have all of this set, let's go ahead and form the DH table again and come up with the parameters. This time I'm going to draw the table myself. This is more customizable, I would say. Okay, so here is my table, and now I'm going to start going from coordinate 3 to coordinate 4 to form my first row. If you look here closely, first question is, do I need to rotate about Z3, which is this guy, this red one, to align X3 and X4? You see the X3 and X4, they look pretty much the same in this video, in this, I'm sorry, in this picture. But if I look at the rotated version of it, they are not the same, right? If I look at the other version, which is from the top, I can see it on the right side, they are not exactly the same. Well, let's see, why is that? So, if you can see here, I had some rotation about this Z3 axis, this one, and it has to be positive like that. Theta 4 it is, that's what we call it. And that made my x-axis to be different. Why? Because if that was Z3, your X3 was like this, okay? But now that it is rotated, your Z4 is not perfectly upward. It is tilted already, okay? So your Z4, and it's not super convenient to draw it here, but I'll try to make it a little bit better if I can. It's not the easiest thing to do on a flat piece of paper, or in this case monitor, to do it. So you have something that is coming a little bit forward like this. And made it something like that, because it is tilted. So now your Z4, or well, actually no. Okay, so here I try to modify it a little bit. And so your Z4 is now something like this. And therefore, your X4 is now something like that. So clearly, with respect to the X3, and if I show the angle of it a little bit, maybe a little bit exaggeration here. With respect to the X3, X4 is definitely rotated by angle theta 4. Therefore, here I have to say yes, there is a theta 4 involved. And then now that that's the case, if you see the origins are on the top of each other, when origins are on the top of each other means no displacement is needed. And if you remember, the displacements are D and A, so I can say without any problem that all of the D's and A's are 0 because all of the origins are on the top of each other. No displacement, all you need is rotation. So between frames 3 and 4, theta 4 will take care of alignment of the x's. Now, are the z's aligned? If you look now, z3 and z4 are not aligned. So you also need a rotation about the new x, x4, to match z3 to z4, and clearly you see the rotation here is 90 degrees, right? Positive 90 degree. About x4 will align z3 with z4. So this is pi over 2 positive. Good, so I went from 3 to 4, now let's go from 4 to 5. So if you look at 4 and 5, let's look at their x's first. Where is x4, where is x5? You see, again, they seem to be on the top of each other, but are they? Again, if we go and look at this case here, this is x3, this is x4, the difference between them is due to theta 4. And if you look at now x4 and x5, clearly, if I can show you x5 on this picture, so it is something like this. Can do a good job of that. And here, this rotation that you had, this rotation theta 5 that you had, is going to be needed to align x4 with x5. So the answer is no, you really need angle theta 5 to align them. And now that you got the x's aligned, what about the z's? Clearly, again, z4 and z5 are not aligned, as you can see here. And so now I have to rotate about the new x, which is x5 now. What should I rotate x5? What should I rotate? Sorry, z4 to match with z5 along x5. Clearly, I have to go clockwise 90 degrees, and clockwise means negative. So there's going to be negative pi over 2 for this one, the twist angle. And then I go from 5 to 6. From 5 to 6, again, clearly there is a rotation involved, theta number 6, which is about this axis. So originally, if you see, your end effector was like this. Let me see if I can do it. So your end effector was something like this. But now you see clearly it is rotated, and that is because there was a rotation about z5 with this angle theta number 6. So you need the alignment theta 6 here for the x alignment. And then do you need to rotate about the new x, which is x6, to align z5 and z6? You see no, because z5 and z6 are aligned the same axis, so no worries about that. That is 0. Now here there is one thing we have to fix, and that is the origin of 5 and 6 are not the same. So the displacement of the last row is not all 0. Okay, when you go from origin of 5 to origin of 6, there is a displacement involved. And this displacement is about what axis? Clearly, you see it's about the z-axis. It's about z5. And the displacement about z5, not x6. It is a d. So this is going to be L and 0. Okay? So we have to pay attention to that. And here, clearly, the d's are the joint variables. So the only variables here, the thetas are the joint variables. The twists are constant or 0, and the L parameter is also constant. So these are the parameters you need for the DH table of the spherical wrist. And again, if you bring that general formula that we had here, correct, for AI, and you plug in everything, I don't need to bring it this time, then your A1 is going to look like, now here you cannot call it really A1, because A1 means the function of theta 1 for joint 1. What you really have here is 4 with respect to 3, so what you really need to call this guy is A4. Okay, so A4 in this case is C4 0, S4 0, S4 0 0 1 0, negative C4, then 0 0, and then a bunch of zeros and 1. Okay, and clearly you see this is not like any regular rotation matrix, although there was a rotation z with theta 4, but because of this twist the axes are basically changed, so that's why you see here it does not look like a regular z or x or y matrix. There is a twist involved. So that's A4, and then you can get your A5, which is going to be of form C5 0, negative S5 0, S5 0, C5 0, 0, negative 1 0, and then 0 and 1. So that is your A5. And finally, you can bring in your A6. And that is going to be like C6, negative S6, 0, 0, S6, C6, 0, 0, 0, 0, 1, L, 0, 0, 0, 1. Okay, so this is your A6 matrix, and now if somebody says, okay, could you determine the position and the orientation of frame 6 with respect to frame 0? So in this case, it is T of 6 with respect to, not 0, 3. Remember here, we don't have the base. We have the base of us is frame 3. So can I determine the position orientation of frame 6 with respect to frame 3? Yes. I need to multiply A4 by A5 by A6. And if I do that, that is going to give me some big thing here. This is going to be cosine 4, cosine 5, cosine 6, minus sine 4, sine 6, sine 4, cosine 5, cosine 6, plus cosine 4, sine 6, sine 5 cosine 6, 0, negative cosine 4, 5, sine of 6 minus sine 4 cosine 6, negative sine 4 cosine 5 sine 6 plus cosine 4 cosine 6, negative sine 5 sine 6, 0, negative cosine 4 sine 5, negative sine 4 sine 5, cosine 5, 0, negative cosine 4 sine 5, that's L actually here. Then negative sine 4 sine 5L, cosine 5L, and 1. Okay, so this big thing here is going to be the forward kinematics equations for a spherical wrist, where this guy is r of 6 with respect to 3, and this one here is d of 6 with respect to 3. Okay, clearly the equations are getting more and more complicated. As you can see, d of 6 with respect to 3 is the function of 4 and 5, correct? The 6 has no effect on it. So this is only a function of theta 4 and theta 5. 4 and 5 will affect the position of the center of the gripper with respect to the center of the wrist. Theta 6 doesn't, because it's just a spin. And in terms of the rotation, you see all three angles, theta 4, theta 5, and theta 6, they all play a role in the orientation of 6 with respect to 3. Okay, so that is your T of 6 with respect to 3. So this is the spherical wrist. This was the cylindrical manipulator, if you remember. And now you might say, what if combine them? What if I bring this whole thing, the spherical wrist with the gripper, and put it at the end of this? So instead of just directly connecting it to the gripper, let's put the spherical wrist here as well. And that is exactly what happens here. This is the cylindrical manipulator with the spherical wrist, and here I just copy and paste everything for you because they are too big. So here, if I want the x, y, z of the end effector frame with respect to base frame, well, these guys I should call them, since n is 6 here, so I can call them 6. Let's see. No, that's fine. So here, this is going to be x number 6, this is going to be y number 6, and this is going to be z number 6. Okay, so now if I want to describe frame 6 in frame 0, which is t of 6 with respect to 0 for the 6th degree of freedom manipulator with theta 1, d2, d3, theta 4, 5, and 6, I should bring in this one here, this one. I should bring this one, and then what? Multiply them together. So this is going to be t of 3 with respect to 0 times t of 6 with respect to 3. Okay, and if I write it like this, like a 4 by 4 matrix, where here I can call them dx, dy, and dz, and 1, and 0, 0, 0, then r1, 1, r1, 2, r1, 3, R21, R22, R23, R31, R32, R33. If I write it like this, where this is my displacement or position of end effector in base, and this guy here is my rotation of the end effector in base. If I say what is dx, dy, dz, and then there's r components, right? There's 12 variables here. What are those in terms of the joint angles? Theta 1, theta 4, theta 5, theta 6, d2, and d3. Then the answer is this guy here. I just paste it. It's just too large to write it here one by one, so I just bring the whole thing for you so you can see that. Okay, so this is what you will get. So now if you look at them, you'll see that, for example, in the location of the end effector with respect to base, which parameters are involved. You see that what I will have is, now there is a D1 here, which shouldn't, we should replace that. And there is also, let's see if there is a D6 involved. Yes, it is. We should replace that. So this D6 here that you see, because my notations in my class lectures are a little bit different. So this D6 has to be L. And let's see, I don't see any other D6. And then I also have a D1 here, and D1 we called it in our notations, what did we call it? We call it L1. So we can call it L1. So this guy is that L1 that I had in the spherical. If you want, you can call this L2, for example, right? You can call this guy L2, then come back here and say, well, this guy is L2 and this guy is L2. And so going back here, this is L2 and these are all L2. Okay, so you have a better notation. So other than L1 and L2, which are geometry of the robot, you see that, for example, if I look at dx, this is a function of what? It's a function of angle theta 1, angle theta 4 and 5, and then the prismatic joint D3. This guy is like a function of something similar, right? Theta 1, theta 4, theta 5, and again D3. And this one is a function of simply theta 4, theta 5, and D2. So you see, it's not like every joint variable is going to affect every position of the end effector or every entry of the rotation matrix of the end effector, okay? Some of them will have some effect on some on the others, some on everything, correct? Like you see here, for example, theta 4 is, or theta 5 is effective on all D components. And if you see them here on the rest of the entries, you see they are also effective on all of the rotation components, R11 to R33, all of these entries of the rotation matrix. Okay, so if you look at the rotation matrix in general, you see that theta 1, theta 4, theta 5, and theta 6, they're all affecting it. Okay, so if I call this a rotation matrix, this rotation matrix is clearly a function of theta 1, theta 4, theta 5, and theta 6. Okay, and that's another interesting thing that you can see, of course. The orientation of the end effector with respect to the base is only a function of what? Is only a function of the angles. The prismatic values D2 and D3 are not going to affect the orientation. They're just displacements. The displacement of a joint is not going to affect the orientation of the end effector with respect to the base. Only the angles do. But what about the position of the end effector with respect to the base? You see everything is involved. Theta 1 is involved, 4 is involved, 5 is involved, D2 is involved, D3 is involved. The only thing that is not involved in this case is the last spin theta 6. Because if you spin this end effector from that configuration probably becomes something like this. But this position of this point is not going to change. So if theta 6 is simply a spin about the last axis, it's not going to affect the position. It only affects the orientation, which you can see here. Okay, so clearly you see they make sense, and now you see they are quite complicated nonlinear functions. There are lots of sines and cosines, as you can see, that are multiplied together. These are multiplied by sine and cosine of the angle, so the equations are absolutely nonlinear, but the good thing is they give you a unique solution. So when I have theta 1, d2, d3, theta 4, 5, 6 for this robot, and I know L1 and L2 from the geometry, it's just writing this equation once, and then each time is plug and play. So at any joint vector, I can find the location of the end effector and orientation of it, so I can see what I'm doing in the workspace. So I can go from Q space to workspace, and that means forward kinematics, right? Okay, so here I wrote some code just now to show you the effect of these angles and visualize the robot for you. So here I chose the two constants of the robot geometry, L1 and L2, to be 280 mils. And here you can change your joint variables. Instead of theta, I use T just to make it shorter. So T1 is theta 1, D2, D3, so 30 degrees, 150 mil, 60 mil, and then 45, 60, and 30 degrees for theta 5, 4, 5, and 6. I calculate my A matrices, I calculate my T matrices, and then I consider my points as circles, my origins, my members as a rigid line. Just for the base, for the origin of the base, I use a triangle instead of a circle, and here I'm going to show you, like for example, when I have these 6 variables. So this yellow member is constant, it's not going to change, the length of it is just going to rotate. So if you compare this, let me run it one more time. If I compare this, correct, you see this one, and for example, I can take a snapshot of that and show you here that, like for example, this is where the angle theta 1 was 30 degrees. Right, so you have this, but then if I go back and change my theta 1 to 0 and run it again, you'll see probably the effect that now you can see here. Okay, so now you can see them side by side. You clearly see the effect here, right? You see that this yellow member was not rotating about the base. Now it does. If you look at the orientations, you clearly see here the orientation of this members is like that, while here the orientation of them, the end effector part, if you look, everything is on this plane now. Okay, so you probably can see a little bit better that there is now some rotation involved. right? If I put that same black arrow I had last time, it is going to be like this. Right? So you clearly see that if this red arrow is the same as this guy, you see that some rotation is involved here, and that is because of the rotation theta 1, right? And you can go ahead and change it to anything you want. So let's say if I set the other angles to 0, you can see the effect of it a lot better. But in general, so this is when all the angles are 0. Everything is straight, right? And if you put it side by side with this one, you can probably see way better rotation theta 1. And then like this is when there is no rotation. Now here I'm going to create a rotation about theta so let me take this and so here again the case of no theta 4. So now I'm gonna do a theta 4. So this guy should change orientation of it, and then probably I would change one of the D's as well. Let's say I make this D2 bigger so it extends up. So here I make this D2 bigger. Instead of 150, I make it like 200. And my theta 4, I make it like, let's say, whatever, 90 degrees to make it visible. Right? And then you can see them now side by side. You see the effect of that. This blue point is now gone up for 50 mil, and you clearly see the effect of the rotation. Right? And then if you want, you can change anything else. So now compared to this one, I can go ahead and do a rotation about the theta 5. So this guy is going to turn left and right. So now I'm going to go and let's say I turn it 60 degrees. Okay, and now you clearly see the rotation here. And you can apply more and more, right? Or you can even do an animation for it. So what you can do is to just put these calculations in a loop and change these parameters one at a time, or maybe all of them at the same time, and then basically update the locations of these guys here. Okay, so you can do that also as an animation and see the effect of each one of these parameters. Okay, so here to make it more interesting for you, I converted my script into a function. So all I need is to each time just call it, give it the input joint angles, and it just creates the plot for me. And so in a script, now I keep calling this function. I pass to it all of the joint variables. Now 5 out of 6 I keep constant, and one of them I keep changing in a loop. And then each time it creates a plot, I do a pause so that I can see it. And then I clean up the axis, allowing for the next one to come. Okay, and here, let's take a look. So here I'm changing the theta 1. Okay, and oh, I guess that's some calculation problem. Let's do it one more time. There we go. Yeah, that's quite interesting. That does it. Ideally, the best way is to update your X and Y data and Z data for these plots and not doing CLA. But you clearly see the effect of theta 1, right? So now if for example, I go ahead and fix theta 1 and then change D2, right? So let's say D2, I go from, let's say, 30 to, let's say, 200 with increments of 10, and I comment that out. Let's see what happens. So it should extend. Oh, it's D2, not D1. You see? That's all it does. It just extends up. Or let's say now I do it to D3. So I keep D2 at whatever number it was, and I change D3, let's say again from 3 to maybe 100. Correct? So now it is just going to extend forward. Yeah, you can see that. And then let's say I want to see the effect of theta 4. So I'm going to change theta 4 from, let's say, 0 to 180 degrees every 15 degrees or so. There we go. You see, that's that rotation. Or I can change, let's say, T5. And T5, I'm going to again change it from 0 to 180. That should be good enough. Let's see. You see? And boom, here I have an impact, right? Because that's what I said. You have to calculate the location of each point on each link and make sure there is no collision. Here, I rotated that joint just too much that the end effector came back and hit the base of the robot or the rest of the links. So that's why this forward kinematics is so important. And let's say for the last one also, I go from 0 to 360. I can do that one without much of a problem. And here you can see that one as well, right? There we go. So in all of these, as you can see, I keep changing the A values because my joint variables are different. The T values the T matrices will be different. And so the coordinates of the points, which are the vertices of that diagram. And so I can create a simple animation like this. So hopefully it was useful to you. And I'm going to finish this video on forward kinematics using the DH convention. Thank you.